I will focus on three codes. Which, as I hope you got from the last talk, is an essential tool for some of the coding schemes. So let's define three codes in a better way, or in a formal way, and then let's talk about several relaxations of three codes and constructions and applications. Okay, so a three code, let me just define. So a tree code So tree code has three parameters. It has a depth, which I will call n. It has an alphabet, which I will call sigma, and distance, which is alpha. So the tree code is just a prefix code. Let's denote it TC from, this is how I set this. Here I mean the set of numbers between 1 and d. Okay, so let's have. Okay, so it's a tree. It's a DRE tree, so each node will have d kids. And the coding will just take a path. A path can be described by a sequence of n numbers between 1 and d, just which child we are taking. And to each such path, it will match a string of length n over the alphabet of the tree. So these will be the labels that I was talking about last time. So this is the first kid, this is the this kid, and so on. So this is just.
This is a prefix code, isn't it just a block code?
No, so it's because, so, okay, remember that I said it's a tree with labels. So it must be prefix code because the labels along this path must be, okay, let's consider two paths. This path and that path. They share a prefix, therefore this, it must be a prefix code. And sometimes, I will definitely look at TC of.
What do you mean by prefix code? Just that the first k bits output, k symbols and output are determined by k symbols of the input.
Right. I mean that the first k symbols of the output are determined by the k symbols, only by the k symbols of the input. And sometimes I will look on x that comes from any such x. I can define TC of x just to be the corresponding prefix of this coding. Okay. Yeah, so maybe it's better to just think about it as a tree, and we have labels. The input is just a path. The output is the labels along this path. So if I have two paths, they share the same prefix, so the labels on that part must be the same.
It's more like online.
Yes, that's definitely an online encoding. Yes, that's another way to do it. Okay, so I just defined the tree. I didn't tell you what tree code need to satisfy. So it satisfies the following. If we take every x of any length, that I will be loose with the length here, and I will take two different symbols, and I will take two different continuation of the same length, that I will call it L. Then we need to the following thing must be satisfied. the Hamming distance of okay, let me say what I just wrote. Let's take any prefix, and then, so this is a path. And then let's make the path diverging, and then continue the path in any arbitrary way. Then the Hamming distance of the labels along the two divergent paths needs to be at least alpha times the length of the divergent path. Let's draw it, because it's very simple. So we have a path x. Then we have to have a divergence. So one path will be sigma, the other path will be sigma prime. And now I allow any continuation, y and y prime. Y and y prime can be the same. Okay, they can be all zeros, or they can be different. I don't care. So this will be y, and this will be y prime, and this is L plus 1. I'm saying that the Hamming distance of the labels on this path and the Hamming distance of the labels of this path and this path should be at least alpha times L plus 1. Questions?
Somehow isn't there some notational confusion? Because if you look at those things, oh, it's the code, sorry.
That's the labels. I encode this path.
And the Hamming distance is happening on the second part, starting from sigma.
So the Hamming distance, okay. The labels of this path is all the labels here. The labels of the second path are all the labels there. But this part is the same. So the Hamming distance here is 0. So definitely the difference can come only from the divergent path. Other questions? Okay, so this is essentially a tree code. And the open question, as I mentioned before, this was formulated asked by Schulman in '93 and still open until today, is construct tree code. Let's rewrite it. Okay, so let D and N and alpha be fixed. And now efficiently construct tree code, or DRE tree code of depth n and distance alpha, if I restrict the alphabet size to be a function of only d and alpha, but independent of the depth. So think of d and alpha as constant. D is 2, binary tree. Alpha is half, let's say. Now for any depth, efficiently construct a tree code of that depth if you're allowed to use only labels which are which is a constant, because these two are constant. So Schulman showed in '93 that actually you can do that for unbounded n. So actually you can have an infinite tree code with just a constant alphabet for any alpha and d. But we don't know how to construct that efficiently. So that's the main problem. And since we don't know how to solve it, how to efficiently construct tree codes, there is not much to talk about tree codes any further. So what I will talk now is relaxations of tree codes and how we construct them and why they are good.
So you didn't mention what is the rate of the code?
The rate.
How does the rate of the code depend on how?
Okay, so the rate, as always, is the input divided by the output, right? Because when we use the tree code, we want to encode each path. Each path is encoded to a label. So the input is n times log d, right? This is how much bits it takes to write a path. And the output will be something like this. So this will be the rate. This is the rate when you use tree code for encoding. What do you do with the tree code?
N is the depth of the tree code?
Yeah, but n cancels.
So what is the kind of existence result? What should be the sigma size in this existence result?
In the existence result, it goes something like this. Am I correct? Yes, that's. So the closer the distance to 1, it's more difficult, and yeah, so it's d to the. But again, if we have a binary tree with some fixed distance, then just a constant. We will not care about.
What is the non-efficiency? So for example, can it be made at least computable for infinite? Can you construct one infinite code, which was computable?
Yes, with okay, it will take. You can brute force. You can always just pick labels.
But if you want to construct an infinite code, we can.
Oh yeah, then you cannot check it.
Infinite code be computable?
No, then it's not constructible. We just have a probabilistic argument that it exists. If it's an infinite, we only have argument that it exists. If it's finite, you can just brute force.
So you mean that the existence of infinite code with any constant thing is not known now?
Right.
So existence is known.
Existence is known, but it's probabilistic argument.
It's not a computable one. Right. So even without any time bound, just an arbitrary computable one. It's still not known.
So there's one of the arguments goes through the local lemma.
And then you can take it.
Then I think there's like I'm not 100% sure, but I think there's like enough flex in the local lemma that we could build it out to some depth and still be sure that you could keep going.
Yeah, I think, I'm not sure, but I think there's a way to probabilistic, with a lot of randomness and so on, you can generate it to a certain depth in a way that, with a guarantee that you can continue it. It has a continuation. I think you can.
Maybe even just with like linear construction. I'm not sure that you would know that.
I
I'm not
think
sure that you
linear
would know that.
construction is one you have. I'm not sure you could do it, but I think.
Yeah, so there are different constructions that may help, but what you had is.
The local lemma you can control that the conditional probabilities are big enough. And so you can basically control that you're tracking the proof of the local lemma in the set file regime. So I think the answer would be yes, but I mean, this is not, this should be confirmed. It's an exponential size object, so you could efficiently test in, so now, maybe we should run the definition, but there's, the efficiency of this question of whether you're constructing a label or the sign address, or whether you're constructing the whole tree. What we're talking about right now, local lemma, you have to be constructing the whole.
Okay. Okay, so that's a nice question. But let's move to more practical things. So efficient constructions and relaxations. Okay, So first I will state a couple of results. So first of all, let me say that if the size of the alphabet is order of log n, right, for some fixed. So again, I will assume some fixed d and alpha. And I claim that if the size of the alphabet is logarithmic, it's not too difficult to construct a tree code. So that's a nice toy example. If you have some time, try to do it. I think it will be fun. Depends on your definition of fun. And somewhat equivalent to this construction, so let me see that I get the parameters correct, yes. So I claim that somewhat equivalent to that, you can take the alphabet size to be constant, but let the distance now be small, and you will still be able to get a tree code out of it. It will be very similar to this, just trade-offing the distance and the alphabet size. And I think Noga will talk about this kind of tree code on Friday. So I will not talk about it. And now I'm going to talk about a k-local tree. OK. So what is a k-local tree code? I'm not going to write the same definition again. I'm just going to tell you where it changes. So it's, again, a tree code, DRE tree code labeled 3. And still, these things have to, this constraint must be satisfied, but only if the divergent paths are of a length at most k. So the difference is that the length of sigma y must be k, or I guess L plus 1 is at most k. So trees that it's still every two divergent paths will have large Hamming distance as long as they are very short. If they are long, we don't know what happens, but if they are short, they work nicely. OK, this is a k-local tree code.
Well, I mean, of course, it's a lot like, of course, the k, I mean, once you have a large Hamming distance, it's not going to get shorter, at least just not going to grow.
Second?
Relative distance as opposed to.
Yeah.
No, I didn't get your question. Sorry.
The alpha factor is not going to.
No, everything remains the same. I just require this constraint only for paths of, only for divergent paths of length k. So why do I tell you about this?
High Hamming rate only for, I think that was the question. Hamming
Well,
rate as
it's
opposed to
clear.
distance.
Yeah. Yes. OK. OK, so why do I tell you about such trees? Yeah. So what is the application of such a tree? And the idea is the following. So let me draw a tree again. So let's assume that somehow we know x. OK? And now something was communicated to us. So there are k communications, k levels of k labels. And assume that we are guaranteed that at most alpha k over 2 of these rounds are corrupted. So the noise is at most this much in this, between that level and that level. If this is the case, then I claim that we can decode y correctly. We know if this holds, and we know x, and we know that in this area there are not too many errors, then we can extend to this point. Now we know x and y, and we can do it again. And this will be very useful for interactive coding. Okay, so again, so why is it? Why is it good for interactive coding? When you use a tree code, the coding will fail only if there are more than that errors. So what is the probability to have more than that error?
Just a random error now?
Random error, yes. So probability of having one section decoded incorrectly. So this is epsilon to, right? And the probability that, so now we take this tree code and run it in a protocol that of length n, and what is the probability that it fails somewhere along the protocol, just by union bound?
As a matter of fact, you already talked about distance, not about decoding.
Yes, but if the number of errors is smaller than that, which happens with this probability, then you will be able to decode correctly. And then you fix your point.
That's part of the condition of this. This is part of the condition.
The condition again, assuming you know the perfects, and assuming that there is not much noise, then you can continue. Okay, so now, okay, my protocol is the following. I will, okay, maybe I didn't say that. So the protocol is the following. I will just, work in chunks of k. Each time I will decode just k. Once I will learn x. Then I will communicate the next part and decode y. And I'm trying to compute what is the probability that I will fail somewhere along this protocol. Is just the probability, right? So this goes like this. Okay, I'm trying to say something very, very, very stupid and simple, which is that if we can take a log n local tree code, then essentially we will have good success in decoding the tree code. Okay, because the probability that there will be log n errors in a consecutive section of order of log n rounds, this probability is very small. Okay? And then just by union bound, the probability that it happens anywhere in the protocol is also very small. So what I'm saying is that a tree code like this is very useful if k is larger than log n, or order of log n. Okay? So now, how do we construct? So now let me show you how to construct a log n, order log n local tree code. Is it clear that this kind of tree will give us something, will give us some object that may be very useful for interactive communication? Okay, good. Okay, so the construction of such a local tree is actually extremely simple. That's also you showed. That's the 2003. Okay, so that's also Schulman from 2003. And the basic idea is the following. So if my tree is very short, is of depth log n, so now n is not the depth of this tree, n will be the depth of our, it will not be, it just, the depth is log n, I can find such tree code efficiently, just by brute force. Because there are only n labels here, and I can just go over all of them and check it, and eventually I can do it efficiently. So I can just run over all the labels and verify that they satisfy this condition,
brute force?
You're saying you can construct if the whole idea is log n, you can do it efficiently. Why?
Why? Okay, so if this is the depth, there are only polynomially many edges. And to check this constraint, I just need to take any two nodes and check that they satisfy this constraint. This is also a polynomial number of nodes. So I can do it efficiently.
So the checking is polynomial.
Efficient meaning polynomial net.
No, the checking is efficient, but let's say so. But you actually want to find it, right? Am I mistaken?
There's only polynomial maybe. Okay, there's a missing detail here, which is one of the existing proofs requires only depth many bits to specify the. Okay, so you don't enumerate over all labeled trees of this depth. That would be too much to enumerate over. But one of the existence proofs has a seed. You know, it's like there's a witness proportional to the depth of the tree. So you enumerate over those and check.
Right, yes. So there is that's partially, there's de-randomization. So you actually don't need to, choose all of the labels. You just need to choose a seed, and this seed is of logarithmic size, and it will generate the entire tree. And the same existent proof shows that one of the seeds must be good. Okay, so now let's assume that we have such a tree code of logarithmic size. Let's say 2 log n, just to be specific. And now I'm going to construct longer tree that will satisfy the local condition. So what am I going to do? The following. So this is depth 2 log n. Let's look on the nodes here that lie on depth log n. There are many nodes like this. What happens now, I will take another copy of this tree code and just prove by picture. I will just concatenate it here. What do I mean by that? I mean that, tree code just give us the label on the path. So the label that goes here will be the concatenation of the label of the white tree with the concatenation with the label of the red tree. So now in the new tree, my alphabet is square the size of the original one. Okay, because I use two labels, one by one.
So now you're trying to show us how to go from log n depth to log n depth, like you
Yes.
have to show how to make it.
Yes. I'm going to make it infinite depth. Okay?
I think local is enough to construct a full thing.
Yes. So is this clear? And I do it independently per node. So, but then I do it again. Now I take this red tree, and again it has nodes and at depth log n, and now I will, let me choose a different color, I will append new trees here. Again, each label in the concatenated tree is just 2 labels of the original trees, because you see, it's just exactly the point that above this point we have the red and the red and the white. Below this point we have the red and the blue. So each one of them is just a concatenation of 2 labels. So now I claim that this is a k-local or log n local tree, and the proof is quite simple. So let's take any path that diverge somewhere. Too many colors, I guess you can see. But recall that the divergent part is of size at most k. And because the divergent path is of size at most k, it means that these 2 divergent paths are fully included in at least one tree code. And because they are fully included in that tree code, it gives the distance to these 2 paths.
The alphabet always increases?
No, it's just This one.
Then you forget the first one and go to the third.
Because this tree ends here. So at each point, you have concatenation of only 2 trees. But this continues forever. So now I showed you how to construct an unbounded tree that has locality log n. And this is very useful. Okay. So how much time do I have? Okay, questions? If not, then I'm going to move to a next relaxation.
So, sorry, can I ask you?
Yes.
So this you can construct deterministically by just brute forcing using Schumann's decree.
Mm-hmm.
And so now you have interactive coding scheme for random error deterministic. Using this.
With success probability 2 over minus log n. It's polynomially
Yeah.
success probability, yes. Yeah, okay, there are extensions to this. Maybe I'll mention them at the end if. With an addition of rewinding or without rewinding, you mean?
So yes, so look at that.
Each type of log is separated by a tree code separately.
So what Nobel is saying is, you said, why do we need to pay local tree? Just take a small depth tree. I mean, it seems like it's useful for random error. For adversarial error, it's not clear.
Yeah, no, for adversarial it will not
But for
work.
random error, why do you need this? Why not just take a copy? So why is this useful for? Actually, is it just a nice inventorial?
Yeah.
So when I know.
No, but there are also extensions. So there is the construction of mark, which I meant to cover, but I guess I will not. And this can be extended to get sub-exponential tree codes of depth n constructed in sub-exponential time. Okay.
So you're suggesting running for like half on the instead and then reinforcing the zero. It's like you have to nail the probability of error on the last few rounds. So you're suggesting padding, like you lose the padding in between.
Yeah.
Sort of, either way, you're suffering some kind of factor of 2 here. You double, no, I should say.
Why can't you just, like Nobel is saying, why just take a chunk of 100 of it?
Run the protocol.
Run the protocol language. Use the tree code. Use hyperbology.
No, that's not high probability, because on the last round, there's probability 1/10, at the very last step, you made a mistake, and now you're not
What
correct.
you have not exponential, whatever you do is possible. Yeah, you have time. You have to do it.
So now you're slowing down by whereas, here you're slowing down a little bit because you're learning the alphabet, because you're more about the tree code, so I don't see why it's necessarily better than the other.
No, it's not one is better. The question is, why do you need that if you have that?
Okay. Okay, so the next relaxation, as known as Potenty Recode. Let me see how I define it. Okay, so I want to say the following. So let me first define what bed nodes are. So I'm going to define the following. So assume that we have x sigma y and x sigma prime y prime that do not satisfy this one. Okay, they don't satisfy the Hamming distance. Suppose we have a tree. It's not a tree code. It's just a labeled tree. So some of the paths will not satisfy this one. I want to say that these nodes will be bad in some sense. Okay? Okay? So what I want to say is define bad node to be any node on sigma y and sigma prime y prime. Okay, so I'm trying to construct a tree code. I don't tell you how, but it will have labels. And you know I will have some divergent paths, and some divergent paths will satisfy the Hamming constraint, and some of them will not. These, for instance, are two paths that don't. Then each node here I will call bad. All the nodes along these two bad paths will be called bad. Okay? And now I'm going to say the following. And alpha epsilon Potenty is a theory tree code. Okay, it's not really tree code, such that so let me write it and then I'll say it. Okay, so I define for some parameter epsilon, alpha epsilon potent tree code to be a tree code if the number of bad nodes in any root to leaf path is at most epsilon n. Okay, so what do I mean by this? Take any path, and now let's count. There will be some paths that collide with it, and all the nodes that collide are bad nodes. So as long as we don't have too many of these, I call this tree potent tree. Right? So yeah, I can just take all the intervals here and union them, and the union of all of these is just epsilon of the total depth. Okay, why can such a tree help us when we do interactive coding? The reason is the following, because it's very high level what I'm about to say, but just to convey the idea. So assume the following. Assume that we were using this tree for interactive communication, and we were communicating the white path. And assume that we reach this point. So at this point, if this was a real tree, okay, in this code, we may be confused whether we are here or here, because there is no Hamming distance. Maybe it's exactly the same labels here and exactly the same labels here. So we are confused. We don't know if we are on the red path or the white path, right? This is a bug in this tree. It's a defect of this tree. But what I say is the following. Let's assume that this was a tree code, and now the labels here and the labels on the red path are totally different. But let's assume that exactly when we were here, there was noise. If there was noise, we are also maybe confused and think that we are on the red instead of being on the white. So what I claim is that any such tree defect is in some sense equivalent to having channel noise exactly at the same spot. And since the total amount of bad noise in any path from root to leaf is just epsilon n, this means that we just increased the channel noise by epsilon. So if we have a scheme that knows how to deal with some amount of noise and uses tree codes, we can just change the tree code into potent tree code and assume, the noise has increased by only an epsilon.
This is adversarial noise.
Second?
This is adversarial noise.
Yeah. It works also for the BSC. Okay. So this is the reason why such trees.
So just that, so indeed, so what is happening is, so wherever you have such a branching, and you have those bad nodes, and what happens that below that root 4, the distance will be big enough.
Right. To know that we are actually here. Exactly. Okay, so the last part is just to claim that we can construct such potent records easily. And the nice thing about them is it's actually very doable. Actually, if you just take large enough alphabet of the size that we showed before, something that goes like, that goes like this, and choose each label uniformly, this will give you a potent record with high probability. Okay, so if for every label here, I just pick it uniformly from large enough alphabet, the result with high probability will be a potent record. So I have less than 10 minutes, so let's just try to prove it. Where is this?
So it's just an existence.
No, this is explicit. It's a randomized construction. Yes, it's random. Yes. It's not deterministic, and
You need to
yes.
quite a large space to store.
So actually, there is a way to reduce the amount of randomness needed to only order of n. So it's very short. So what happens in this case, one party will just draw order of n bits, send it to the other side. They will construct a tree. This doesn't increase the rate, so it's doable. Okay, now I have the size. So we take something like this. Okay. Okay, so again, I assume now that I construct the tree by just picking each label uniformly from that alphabet. Now I'm trying to compute what is the probability to have such a colliding path, let's say of length L, or L plus 1, just to be, because I used L plus 1 all the way. So I'm claiming that the probability to have collision of length L. Okay, don't kill me if I lose the plus 1 somewhere. So what is collision? It just means that these two paths don't satisfy the Hamming distance, right? It means the probability that x sigma y, okay, the Hamming distance, Hamming of the encoding of this is less than alpha L plus 1. Okay? And how many, so let's fix our path, and now we want how many different colliding paths we have, how many ways to choose sigma prime and y prime. We have d to the L plus 1 such possibilities. Okay? So what is the probability to not satisfy this? And excuse me if I'm not very accurate here. So it's just we can choose all the indices that are that are the same, right? And this, so the white path is fixed. The red path, I will just choose which indices are the same as the white, and this is the probability that they will be the same. I need to pick exactly the same label as in the white one, so we have 1 over the size of the alphabet to pick exactly the same index, right, times this. And if we do the math, and I'm not fooling you too much, so this gives us something like this. Okay? So you can see that if I take my alphabet to be large enough, I will be able to make this probability very, very small, something like d to the minus L. Okay, so this is the probability that just two paths that we will have something like this of length L. Now I need to, just to complete it, I need to say what is the probability that we have more than epsilon n such colliding paths, so that the total length of them will be more than epsilon n.
What is the probability that you have any form factor?
So the probability to have 1 in a fixed place, or just to have 1, is what we computed there. And this one gives us L plus 1. So now I will try to compute what is the probability that I have such colliding paths such that the union is more than epsilon n. Okay? Probability of more than epsilon n bed nodes. And again, I'm not being very accurate here. So if those colliding paths were disjoint, things would be easier. Okay? So let's assume they are disjoint. There is a nice lemma that says that if you have union of intervals of length n, some n, then you can find a disjoint union of intervals whose length is at least n over 2. If you have intervals whose union is n, you can take out of them subset of intervals, which each interval, they will be disjoint, so no two intervals will intersect, and the total length of their union will be at least n over 2. It's not too difficult to prove that. So now I can just assume that all my colliding paths are disjoint in the tree, and let's assume that they will have length L1, L2, Lk. All of them are disjoint, and the sum of them, I can assume that it's more than epsilon n over 2. And now just because they are disjoint, this is just the probability to have collision of length Li. And this is exactly what we computed here. This is just d Li over epsilon. I'm forgetting constants. And this is just d to the sum of the Li's. Of course, there's a minus. And since their sum is epsilon we assume that their sum is more than epsilon half, this will be something like this. Okay, so this means that if we just pick each label uniformly, randomly, the probability that we will fail is exponentially small.
You will have to multiply by the number.
Yes, but I was hiding here a constant, so let's make the constant 8, and then let's just, this is the number of paths, so it doesn't really matter. But you're right. Okay, so the probability to fail is exponentially small, so with extremely high probability we can get such a potent tree. I guess I'm over time, so I cannot describe any more relaxations. So I guess that will be it. Thanks.